Welcome to Study Loop.
Hello everyone, today we're doing chapter 14, problem 20, and this problem asks us how many signals are present in the proton NMR spectra for each of the following molecules. What's the splitting observed in each signal? So let's start with A, this one over here. So we know right away that these terminal carbons have 3 protons each that we can all draw out. And we know that following the octet rule, this carbon has 4 bonds, so there's no protons attached to it. This carbon should have 2 bonds here, 2 hydrogens here. So if I'm interested in identifying the splitting patterns and the number of peaks for each proton, the first thing I need to do is identify the number of unique chemically distinct protons I have. So we know that this is a sigma bond here. So these 3 protons can rotate, and you kind of get a blurred effect of all 3 of these. So these all act as if they're in the same chemical environment. Next, we have these 2 protons here, which is bound to the same carbon, and then we have finally our alcohol proton here. So if we start from the left, if we see that, if we're looking at one of these examples, we see that we're interested in these 3 protons, and I want to know the splitting pattern. So neighbor plus 1, so I'm looking at the neighbor carbon here. We have 1 neighbor carbon, and how many protons attached to us? Well, 0 protons, so it's going to be 0 plus 1. So we're going to have a singlet here. So these 9 protons are going to be represented by a single peak in our NMR spectra. Well, what about these 2 protons here? Well, these 2 protons are bound to the central carbon, that's bound to an oxygen and bound to a carbon. The oxygen, so the thing to remember is oxygens and nitrogen protons do not split other signals, and they're not split by adjacent protons. So even though this oxygen is bound to a proton, you can only do splitting from carbons and not oxygens or nitrogen. So that's something, a key thing to keep in mind. So even though yes, there is a proton attached to this oxygen, it's not involved with splitting these H's off the carbon. So the only other hope is to look at this carbon here, which is also neighboring the carbon that we're interested in, but there's no protons off this carbon. So neighboring equals 0 plus 1 equals a singlet. So these 2 protons would equals a singlet. And once again, protons of amides or amines, nitrogens, and oxygens do not split. So right away, we know that this is also going to be a singlet. So we have 3 distinct protons. So we're going to have 3 signals, each of them being a singlet. And now if we go on to the second problem, and we draw out all our protons, so now we see that we have 3 unique different types of protons because each of these protons exists in its own chemically distinct environment. So we know that we're going to have 3 protons from carbons, but then we also going to consider that we have this alcohol proton. So in total, we have 4 different types of protons. So we know that we're going to have 4 unique NMR signals. But what about the peaks corresponding to each one? Well, if you look at this terminal protons here on this terminal carbon, we see that this carbon is neighboring one other carbon here. Attached to this carbon, we have 2 protons. So n equals 2. So we do n plus 1. 2 plus 1 equals 3. So we know that these 3 protons are going to be represented by a triplet. Now what about these 2 protons? Well, these 2 protons are bound to the central carbon that's bound to one type of proton on the left and another different type of proton on the right. So it's bound to 2 different types of protons. And if you guys remember from previous examples, there's an equation that we got to multiply the effects by each. So using the n plus 1 rule, so the equation for the number of total possible number of peaks we'll get for these 2 protons is n plus 1 times m plus 1. So m is just the different types of protons. So n m n are different types of protons. M is the red proton, n is the green proton. So if I follow the rule, we have how many protons neighboring on the left? We have 3 plus 1, so that's 4, times, what about m? So we have another neighboring carbon on the right, and this neighboring carbon is bound to 2 more protons. So we have 2 plus 1 equals 3. So this one will have a maximum possible of 12 peaks. So this will be a multiplet here. And now, what about these two protons down here? Well, these two protons are neighbored by an oxygen. Remember, oxygen doesn't matter if it has a hydrogen or not. These are not involved in splitting, so we just cancel that out. And on the left side, we have a carbon that has two protons bound to it. So neighboring equals 2 plus 1, so that equals 3. So we'll have a triplet here for these two protons right here. And obviously, this hydrogen is not involved, the oxygen's hydrogen is not involved in any splitting, so we have a singlet here. So in total, we have a triplet, singlet, and a multiplet, corresponding to 4 chemically distinct protons. And now let's look at this last example here. So once again, draw out your different protons. So we see that we have 3 types of protons, blue, green, and black. So let's start with blue. So we see that both of these protons are neighbored by 1 carbon, and this carbon has 1 proton neighbor. So we have n plus 1, so 1 plus 1 equals 2. So these 6 protons will be represented by 2 peaks, being a doublet. Now what about this central carbon? Well, this central carbon is neighboring to 2 carbons and a nitrogen. Nitrogen is not involved in splitting, so we can just ignore that. But these 2 carbons are each bound to 3 protons. So because we have 2 different neighbors, but they're not actually in chemically distinct environments, these are identical neighbors, as you can see by both being blue colored. These are identical neighbors, so we do not use this equation. We just use the n plus 1 equation, and we consider all of these protons equivalent, so they all are the n type of protons. We don't have any m types of protons in this example, because these 2 neighbors off of the central carbon are identical. So because of that, we see that we have 6 neighbors plus 1, so we get 7. So we get 7 peak signal for this middle carbon here. And obviously, these 2 protons, once again, nitrogen and oxygen protons do not split, so we just get a singlet for this one. So in total, we have 3 different types of peaks, one being a doublet, one being having 7 peaks, and one being having 1 peak here for the nitrogen protons.